Hey everyone, I hope you're doing well. I miss you all. I am really glad everyone did fairly well on the tests that we took, and for the most part, everyone's in pretty good shape. So I hope you guys are all surviving distance learning. We're going to change it up a little bit this week. I know that it's very difficult because you guys have to log into a lot of different places, and you're doing bookwork and you're trying to submit it. So I'm taking a play out of Ms. Baker's playbook, and we're going to try to do this through Google Forms. So the way this is going to work, your assignment's going to be in 3 pieces this week. We're going to do what would replace the book questions. I'm just going to give you this lecture, and there are some questions in the Google form, so you'll fill those out and send them, and then you'll be done. We'll have USA test prep like we always do. And then you're going to do something that's called the WAVE summative assignment. So a summative assignment, for those that don't know, that's your test category. And obviously, you guys did take the test through USA test prep. That's probably not the most fair way to evaluate. And so therefore, I was trying to figure out something that was sort of project based. And I know that you guys are getting a lot of projects and you're probably a little sick of it. So what we're going to do is every week you'll have sort of a mini test assignment. So for this week, what you complete, you're going to read an article and then you're going to answer some questions about it. And that's going to count for 1/4 of a test grade. So every week we'll have one assignment that falls in that category. It'll count for 1/4, and then at the end, over the next 4 weeks, and then we'll be done with school. That'll count as your final test grade. So hopefully that works out. All right, so we are going to get started. We're going to talk about waves. This is like the 30-second theater version of what you would have gotten in class, but I just wanted to hit the key points so that in the future, if you need to know about waves, that you'll be able to recognize some of this. Okay, what is a wave? A wave is a rhythmic disturbance that transfers energy through matter or space. So one thing to understand about waves is that it carries this energy without carrying matter from place to place. So it's not necessarily moving matter, it's moving energy without moving the matter, which is one of those concepts in physical science that kind of makes your brain hurt a little bit. And so we're going to talk about how it transfers that energy through our study of waves. Classifying waves. Waves can be either electromagnetic or mechanical. So electromagnetic waves are waves capable of transferring energy through a vacuum. An example of this is light waves. So my face is blocking the picture a little bit, but there's a picture of an astronaut over here, and he's actually taking a selfie. And the cool thing about that is you can take a selfie in space because light waves do not need matter or particles to travel through. They can travel in that vacuum, and space is a vacuum. However, mechanical waves are waves that can only travel through a medium. A medium is matter through which a wave travels through, can be solid, liquid, or gas. So while this guy over here can take a selfie in space, he cannot talk on the phone because sound waves and water waves are the kind of mechanical waves that can only travel through a medium. So because there's no gas or anything in the atmosphere, you can only transmit electromagnetic waves. You can't transmit mechanical waves. A good way to remember the difference between the two is mechanical waves and medium both start with the letter M. So mechanical waves need a medium. Electromagnetic waves do not need a medium. So how do we classify waves? So waves, in addition to being either electromagnetic, magnetic, or mechanical, can also be transverse or longitudinal. A transverse wave is matter in the medium moves back and forth at right angles to the direction that the wave is traveling. Particle motion is perpendicular to wave motion. An example is electromagnetic waves, vibrations in string instruments, and ripples on the surface of water. So what in the world do we mean by that? So you probably have learned in either a math class or somewhere along the line is that perpendicular is something that forms a right angle. So in the case of this wave, the motion of the wave is going this way. However, the motion of the actual particles themselves are going this way and this way. And so this is kind of the wave is traveling through space this way, so the direction is going this way, but the wave itself is moving up and down. The other kind of wave is a longitudinal wave, and that's a compressional wave. And so this is basically like a slinky. So matter in the medium moves back and forth in the same direction that the wave is traveling. Particle motion is parallel to wave motion, and examples are sound waves, ultrasound waves. I'm going to cut this off. Waves made with a slinky. So you can see If this was a slinky, you know that if you, all right, so we had a little technological struggle there. So what I was trying to say is that, you know, when you send a slinky, let's say they're sending it across the room, the slinky itself, the spring, is going to make this kind of motion depending on which way. So that each of the rings are kind of moving together this way, and they're moving along with the wave. Okay, so labeling parts of waves. In transverse waves, we have a crest. So that is the peak, the highest point of the transverse wave. So that's all of these little peaks here, little top of the hill. The trough, and you can kind of remember it if anybody has animals or horses or anything, a trough is a water bowl, or like the big water tank that the horse drinks out of. And similarly, you know, it looks like this on the bottom, you know, obviously, or think of it like a bowl. So the bottom of the bowl would be the trough, and that's the lowest point of a transverse wave. So crest is the top part, trough is the lowest part. The labeling parts of waves and the longitudinal waves looks a little bit scarier, but it really isn't. So this is kind of a good reminder that when you're looking at a wave, we think, you know, I compared the longitudinal wave to a slinky, but in actuality, wave is a movement of particles. So it's not going to be rings coiled up. It's going to look a lot more like the diagram on the top there. So a compression, you know, when something is compressed, is where things are pushed together. So that's where particles are pushed together in a longitudinal wave. So if you saw a picture of a longitudinal wave, it may look like this. And this segment here is a compression. So these particles are closer together. And so that would represent sort of the solid part of the slinky. See, it says compression. The rarefaction, and that's a word that you probably have never heard before, is the part in between. So where particles are spread apart. So that's going to be this area here where the particles are further apart, and also like the white part, which would represent the space of air between the springs of a slinky. When we're measuring waves, we're talking about the amplitude. The amplitude is the amount of energy carried by a wave. In a transverse wave, this is proportional to the height of the wave. So if you have a higher wave, if this is, let's say there was, oops, okay. Let's say that there was another wave here that looked like this. This is a crazy wave. Okay, so because this is a higher wave, we can assume that it is a higher amplitude, which means it has more energy. This one, because it's not as tall, has a lower energy. In a longitudinal wave, it's proportional to the amount of compression. So when the particles are closer together, it has a higher energy. So if there are more dots in this area here, that is going to correspond to a higher amount of energy. The wavelength, this is signified by the Greek letter lambda, and it's the distance between one point on a wave and the nearest point just like it. We measure it in meters. In transverse waves, it's crest to crest or trough to trough. And what we mean by that is it's the distance between one point on a wave and the nearest point just like it. So these 2 points, I'm getting a little pen back here. Oops, not that one. Okay. So these 2 points, this one here and this one here, look just alike. And so this would be a wavelength. Similarly, this trough and this trough look just alike. And so that would also be a wavelength. On longitudinal waves, it is compression to compression or rarefaction to rarefaction. So compression to compression is the first one here. This is one compression. This is another compression. So this would be a wavelength. Trough to trough, where there's less energy here, right here, and right here, where there's less dots here, that would also be a wavelength. Some more vocabulary to do with measuring waves. So as you guys might be starting to suspect, because we're talking about the units of measure, yes, we would have done some math to do with this. If there's anything that is a silver lining to a global pandemic, it's that you don't have to do as much math in physical science. So it's not all bad. Okay, so period, uppercase T, and that's the amount of time it takes one wavelength to pass a point. We measure it in seconds. And then the frequency, and this is designated by what my high school physics teacher used to call the fancy F, is the number of waves that pass a given point in 1 second. We measure that in hertz, which is probably a term that you've heard before. And a hertz is equal to 1 over seconds, or second to the -1. Frequency and period have an inverse relationship. And so In a high frequency wave, the period is shorter. In a low frequency wave, the period is longer. And that's all we're going to talk about on that because I don't want to get you too hung up on the terminology. Frequency and wavelength also have an inverse relationship. The higher the frequency, the shorter the wavelength. So over here, we have a high frequency. There is, as this wave is progressing in this direction, the amount of times that one wavelength passes a given point. So if these waves are progressing this way, it's going to pass this given point more quickly. At a low frequency, it has a long wavelength. So if this is the point at which we're referencing, let's say the wave is going this way, it is going to take a little bit longer between each of the humps to get past that point. The lower frequency, lower wavelength. All right, a little more vocab. Wave speed is lowercase v, and this is how fast the wave travels. We measure it in meters per second. Speed is dependent on the type of wave and the properties of the medium the wave is traveling through. So when we're talking about medium, we're talking about material that these waves are traveling through. We remember that medium and mechanical both start with the letter M, so we know that mechanical waves are the ones that need a medium. They must travel through particles, and therefore they travel fastest through a solid. Why would they travel fastest through a solid? Well, we know that comparatively, particles in a solid are really close together. In a liquid, they're a little further apart, and then gases, they're much further apart. So it has to do with the closest of the particles. If the particles are very close together, the waves are going to be able to travel more quickly because it's more efficient for them. They also travel through warmer mediums. Now, could you think about why that would be? Because when things are warm, so if there's something at room temperature and the particles are moving like this, and then you heat that up, the particles are going to move more quickly. So the particles are colliding more. When they're colliding, it's presenting an opportunity for that wave to transfer that energy, and that's how that happens. Electromagnetic waves like light do not travel through a medium. They travel through a vacuum, and therefore they are the slowest through solids. So basically, those particles are too close together for that electromagnetic wave to find an efficient path because it's looking for a vacuum. I want to push those particles out of the way. No, thank you. So in this way, mechanical waves and electromagnetic waves are a little bit opposite. Mechanical waves travel really well through a solid. Electromagnetic waves do not. So now it's time to talk about behaviors of waves. I'm going to run through these really fast. We could spend a whole lot more time on them, and I wish that we could, but I want to make sure that I don't give you guys a 45-minute video. If you are more curious about this, you can certainly, I will post the chapters that correspond in your online textbook, and you can kind of read further about it. Reflection is probably the one that we're most familiar with. So reflection, we know if we go to somewhere to a pond or a lake and it's a nice sunny day, you're going to see something that looks like the picture that we see here. And so it looks as if there is a perfect mirroring from the clouds and the mountains down onto the surface of the water. So a reflection is when a wave strikes an object and bounces off of it. But reflection is not just for light waves. All kinds of waves can do reflection. So echoes are an example of a reflected sound wave. So if you are in the right environmental conditions and you holler out, whatever you have yelled out is going to come back and you'll be able to hear it. So all kinds of waves can do reflection. We're going to very lightly touch on the law of reflection. We're about to talk about some angles. I know that you guys, your blood pressure is rising already because this is getting too close to geometry, so just bear with me. The law of reflection, which is really the takeaway from this slide, is that the angle of incidence is always equal to the angle of reflection. So what does that mean? That means that the angle at which whatever wave comes in, whether it be sound, light, any other kind of wave, angle that it comes in on is going to be the same angle that it leaves on. So the reflecting surface, let's say that is the surface of the lake. The incident ray, so that's the light wave coming in, is going to hit the surface of the lake and it's going to bounce off at the exact same angle. Refraction. So we've all probably seen something similar. So the way this fish is pictured, it looks like it might have two tails. Does it actually have two tails? No. Refraction is responsible for this behavior. This is also why if you take a pencil and you put it into a clear glass of water, the pencil, when you look at it, will appear bent. If you've never done that before, I encourage you to do it. You may have already run to your cupboard to get a glass now, but it does happen. And that's refraction is the bending of waves caused by a change in its speed as it moves from one medium through another. So in the case of this fish or in the pencil, the light waves are traveling more quickly through the area on the surface. So where we see the little fishy's eye pop up, those light waves that are then going into being registered by your eye are traveling through air, whereas the light waves in the water are traveling through the water. So the light waves that are in the water are going to be traveling more quickly because there is more opportunity for those particles to touch. It's going to travel more quickly in the water than it would in the air. So that's refraction. That's why things often look bent if they're in water or if they're in two different mediums. The greater the change in speed, the more the wave bends. So for example, if you have a bug or something that's been preserved in one of those clear prisms and a part of it was sticking out, there will be a greater level of bending than what we see here between the air and the water for the fish. And the reason is because there is a greater distance between gas and solid than there is between gas and liquid. We're going to talk really briefly on how prisms work. I don't want you to get really hung up on this. Light waves enter into a prism and they slow down. So that's they're traveling through the air. They're hitting that solid, or I guess they could be traveling through water, and then hitting that solid, which is the prism, and it's slowing down. Because they are slowing down due to this change in medium, it causes those waves to bend. And as they are bending and moving through that new medium, they, for the example of visible light, that's why we go from the white visible light to the rainbow pattern. The different colors of light bend different amounts, and thus the colors are separated. And this is because each color is a different wavelength, and we'll talk about the electromagnetic spectrum and a little bit more about colors later on. But the takeaway from this is the reason that we get a different color on the other side of the prism is because going through the prism slows that down. Classic real world example, rainbows. We see rainbows in the sky because the light is hitting droplets of water in the atmosphere, and then the visible light that is registering with our eye is in that pattern of the rainbow. That's also why if you look down at a rain puddle under certain conditions, it looks like there is a rainbow on the ground. It's because the light is being bent through those water particles, and that's why you're seeing rainbow color. All right, diffraction. This is the one that for me personally is the most difficult to grasp. It's probably the one that I've had been familiar with the least when I first learned about it. So diffraction is when an object causes a wave to change direction and bend around it. Amounts of diffraction depends on the size of the object, the wavelength of the waves, and so let's break that down into real world examples. So let's say it's an evening time. You're in your living room and you don't have any lights on. Maybe you've got a younger sibling or somebody sleeping, taking a nap, and you're sitting there watching some TV or playing on your iPad, and the street lights come on, and from the street light comes through a little tiny crack in your curtain and then shines on the ground. And so we know that there is a large source of light, so there are a lot of light rays, but as they are coming through that tiny crack, what's visible on the floor is just a really tiny crack of light. And so that's because of diffraction. Those light waves actually had to bend around that curtain to get through that little tiny space to get on and shine on your floor. However, if there is a loud conversation going on outside, chances are you're going to be able to hear it relatively well inside. If there was, of course, there would be a glass window there, but if, let's say, there was only that cloth curtain there, you probably would be able to hear it almost as well as if you were standing on the same side of the curtain with them. And that is because sound waves tend to diffract better than light waves because they are bigger. So because they are bigger, they have more area to bend and therefore are better at bending because they're just bigger, they're longer. All right, absorption. This one is pretty straightforward. So when a wave strikes an object and goes into it, the easiest thing I can think of is when we get warmed up with rays from the sun. So energy from the wave gets converted to thermal energy. So light from the sun hits our bodies. Those light waves are absorbed into us, and then that converts to thermal energy. Light is more attracted to dark colors, and that's why it's better to wear dark colors in the wintertime and light colors in the summertime. If you're outside in the summertime with a jet black shirt and it's 99 degrees, you're going to have a big sad. You're going to be very, very hot. And the reason for that is because those light rays are literally being absorbed by your body and changing into thermal energy. Interference. This is a really cool one. So that's when two waves come together to form a completely new wave. There are two kinds of interference. There's constructive and deconstructive. So constructive interference is when two or more waves are added together and basically make into a bigger super wave. The like parts of the waves must line up, so they must kind of like stack into one another, almost like an egg crate, and then they come together and they form a bigger wave. This results in an increase in the amplitude of the wave, We know an increase in amplitude means that there's more energy. And if this was in the case of a sound wave with a higher amplitude would have more sound. This is exactly what's happening when you are at a concert or listening to someone speak or a school assembly, and somebody with a microphone gets too close to one of the speakers and you hear that loud wah sound and everyone goes, ah! That is because of constructive interference. Those two waves have come together, they have joined forces and formed a big wave and made a really, really loud sound. The opposite of that is deconstructive interference, when two or more waves subtract from one another when they overlap. So this is, if you're thinking about in terms of an egg crate, it can either stack nicely, or if you move it over slightly, it's not going to compress into one another, it's just going to stack on top of each other. And so that's what's happening when deconstructive interference happens. This is the science behind noise canceling headphones. The headphones are emitting sound waves, and the sound waves of the surrounding noise around you are being canceled by that. And that's very, very cool science that goes into noise canceling headphones, and that's how they work. Resonance is the last one. Resonance is really difficult to teach about without being able to use tuning forks in class. It is the process where an object is made to vibrate at its natural frequency by absorbing the energy of another object that is vibrating at the same frequency. So if you have two tuning forks that are for the same musical note, like musicians use these a lot, and so that they are trying to bring their instrument into tune with the tuning fork that they know is vibrating at a set frequency. So just know that an example of resonance is a tuning fork, and that is about as far as we're going to get into that. All right, guys, I hope you have a great week. If you have any questions, I'm going to leave a spot on the forum for you to ask them. I can address them in my next video. If you have any questions, please hit me on Remind or send me an email, and I will see you guys next week. Bye.